Hello everyone and welcome on this video. The topic of this video today is to show you the integration between Altair tools, namely HyperWorks, OptiStruct, HyperView, and our software EikoTwin DIC. The goal of this video today is to showcase how simple it is to transfer a mesh and a simulation result from HyperWorks to EikoTwin DIC, to compare that to DIC results, and then back into HyperView for visualization. So here I have a very simple model. It's an elastic model here that you can see on screen. This shape is optimized shape to withstand the load that you can understand here by looking at the boundary conditions. There's a fixed boundary condition here, and then there's a moving part that goes closer to the other one along X. And so this shape has been optimized in order to withstand this load, which incidentally ended up looking like a croissant, which is pretty fitting for us French people. So we kept this shape, we kind of like it, and we've produced this simulation of it. So if I can import this simulation into HyperView, you will see that here I have full simulation model, one step, very simple, of this part, and then this X displacement field that goes in this direction. If you want to look at this component, you will see that they're getting closer together, definitely. So we have this kind of idealistic, maybe loading path, and we want to make sure that what happened in the test is exactly what happened in the simulation, or we want to locate the differences between these two versions of this part, the digital version here and then the tested version. So in order for us to do that, we're going to let's build another project, start another project in EikoTwin DIC, and just load the images that we took during the test. We took a series of 7 pictures here of a speckled part, which is 3D printed. And this very simple setup here allows us to get these feet closer together. You can see that as in general with digital image correlation, the surface is patterned with spray paint. If you're interested in digital image correlation, you can look at a lot of resources on our website. Here, the goal is not to explain what digital image correlation is. I'll just tell you, for those of you who don't know it, that this is an image processing technique that allows to follow this pattern here in order to measure displacement and strain fields, which is what we're going to do today. Maybe something that I should tell about EikoTwin DIC is that it is software that specializes into validation of FE models based on DIC measurement and also all other measurements as well. And the way we do that is that we link the mesh that we have here. It's the H3D mesh of the croissant file that really looks like what the pictures have. And this is exactly the versions that comes from this, this H3D file directly from HyperMesh. And so we have this this shape here, this 3D model here of the part, and we want to create a link between this part and the images, which is what we're going to do here. We're going to select very simply measurement zone, which is just simply the surface of this specimen, and we're going to make a link between those two parts by selecting features that can be spotted both in the mesh, which is on the left, and in the image, which is obviously on the right. Here, the spot is pretty convenient for that because we have recognizable features. Might not be exactly the case for every one of these of the structures that you're working with, but I'd say that's probably reasonable to find some of these features. We usually don't struggle too much to find features or to mark features onto the specimen. In order for the software to make a link between what is seen by the camera and what is seen by the eye on the left part here on the mesh. So when these points are selected in the camera frame, we project the mesh onto the image virtually to make sure everything fits, which I think is not too bad for a first try. And then each one of these surface elements here is going to follow that little bit of texture in order to measure the displacement field and to then calculate the strain field. This is the main step here for 2D DIC because we only have one camera. A little bit more complex for 3D DIC because the calibration process needs to understand where the cameras are with respect to each other, but here we don't have to do that. The displacement field can then be calculated. I'm just going to fix this parameter here, kind of a filtering length, and then run the simulation, the measurement. Sorry, there's no simulation here. I should tell you about that. This is a mesh, but it really isn't a simulation model. This is really just kinematics measurement, which is why it was a mistake to say it is simulation. So here, step by step, image by image, the measurement is being done, and here we can, start looking at the first image's result of XY displacement. Here I have X. Here I can also look at the Y displacement. I'm sorry for the warp factor, and then obviously on the Z or Z coordinate, depending on where you live. The displacement field is 0 because obviously we only have one camera, which is fit for 2D DIC, but obviously not for out of plane stereo or multi-camera view, which is not the topic of this video today. So we can also look at while the simulation, measurement is running. We can look at the strains that are measured by the algorithm here. So here, for instance, if I, click the wrong box here. If I set the right color bar here, for instance, would this work? Not even sure. We'll see. Yeah, this is a little bit too dark, I think. Yes. So you can spot at the look at the strains that are measured here against the measurement. You can see the areas that are in compression and the ones that are in tension, which is something pretty natural for the DIC, but still interesting. And obviously, you can compare that to the simulation model. So the first way you can compare a simulation model to a DIC measurement here within EikoTwin DIC. You can load the simulation result. Here I load the same the content of the same H3D file that I've loaded for the mesh, and then say, okay, my first step is actually time equals 7 seconds to synchronize both data sets. And this way, it's going to be imported onto the mesh, and then I can make a comparison between measurement and simulation. This comparison is one-to-one because it's the measurement we've done on the surface mesh here, and we have the simulation result here on the full. I'll go back to displacement X, the full structure here. We have the displacement of, and now obviously when we put the DIC measurement on top, we see that there's probably a difference between these two. And this difference we can estimate from the difference field. For instance, here on X, you can see where there's a difference and where there's the same. Obviously, you can adjust the color bar if you want to look at details more closely. But something that I like to do is to use the warp factor here to understand the global behavior of things. And you can see that if you look only at the simulation mesh, Obviously, you're going to see a straight displacement of the foot along X, which is naturally not the case exactly in reality, especially depending on the setup that you have. It's this one's not very rigid, and so you can see there's clear signs of rotation here, which makes it a little bit different than the simulation model. So you can spot the differences in displacement, and then obviously in strain you can do the same. I won't adjust the color bar here, but you get the spirit. Something nice also about this interface is that you can compare both displacements, also with what we call virtual sensors. So for instance, if I create here a displacement sensor D, here I put it right here for the sake of simplicity. I can create a graph, and then within this graph, I will be able to plot both information, the simulation and also the measurement, which, here I took sort of an arbitrary time scale, but you can see here there's a spotted difference. It's pretty clear. And you can do it also, if you don't want to look at X, you can look at the virtual displacement as well, which will show you there's obviously no displacement or barely no displacement in the simulation, whether you can spot one very clearly in the measurement. Which is actually kind of a side point here, but is pretty symptomatic of structural simulations in general, is that they simplify boundary condition for lack of knowledge, which is normal, but these are problems we spot very often. So we have that comparison within EikoTwin DIC, but you might want also to compare results within your favorite prepost, which if you did the simulation in OptiStruct and exported an H3D file, it's probably HyperView. So you can export displacement fields. Here it's actually going to export pretty much everything, displacement and strains. And here, not as a CSV file, but as a HyperWorks ASCII file, which is something that is readable by HyperView. So I have just exported this ASCII file, and then I'm going to do the same thing as I've done before, which is locate this file I've just exported. Here it is, and just say, okay, let's apply this, loading operation, and then you can directly plot what you've measured onto the mesh within HyperView. And here you are. You have all of your result within HyperView, so you can do all kinds of post-processing operations. You can try and match the measured data set with the simulation. You can do all sorts of things. I'm not the best user of HyperView, so I'm not going to display that, but you can probably imagine what you can do if you're a HyperView user. Okay, I think I'm done for today. Thanks for watching the video, and yes, hope you enjoyed it, and don't hesitate if you're an Altair user to check out the APA, which is the Altair Partner Alliance, on which you can download this software, EikoTwin DIC, and try and use it for your own needs. Of course, if you need some help, don't hesitate to call us. Thank you. Bye-bye.